Hello everyone. So we continued our lectures on surface Plasmon Polariton. In the last lecture we derived this Helmholtz relation and now knowing the form of the electric field as shown here, we had arrived at these two relations for the two regions. The first one is in the dielectric region, this is in the dielectric and this in the conductor. So Z less than 0. One thing has to be noted, there's a slight typo, the epsilon 2 has to be different. So in the dielectric it is epsilon D and in the conductor it's epsilon C. Okay, so these are the two dielectric constants and so on. So we carry on from here. So the way, what is our aim? Our aim is to find out the dispersion relation for this sort of, these plasmons, I mean for this system. So for that we have to solve for the electric fields and magnetic fields and see what all, put in the boundary conditions and get to the final relations. This is one of the relation we get. This comes from the wave equation. All we had done is given electric field of this form, we know this the initial formulation of the wave equation leads to this sort of equation. So we do find that there is a relation between kx and kd and epsilon d, and also kx and kc and epsilon c. So this is where we keep these relations. We will get back to these again. And now what we do is we do a standard, this is a very standard formalism. So other than that curl of curly relation, we have the independent relations for the curls. So we have typically from the Maxwell's equations, we pick up two of them. One is curl E, which is minus del B del T, which is minus mu naught. We'll write everything in terms of E and H. This is one relation, and of course there's the other one in form of curl of H, which we will come a little later. Now from these relations, what we will do is we will break up in the various components, the x cap, y cap and z cap components. Please note that the way we have defined the electric field, so it is a function of x and z and time, right? And this we can also write as some E, which is a function of x and y, and the time part is nothing but exponential minus I omega t. Okay, now but if I look into it as the components, it is basically Ex, Ey and Ez, and that is exactly what we are going to solve. So knowing this form, we can start with this curl relation, and what we get is for the x hat, I mean the x component of this curl term, we have I hope you're all familiar with this. Y is equal to whatever we have on the right hand side, which is mu naught del H x del D. Okay, and the left hand side, this term is 0 because it is independent of y. So what we are left with is minus mu naught, and the derivative with respect to time will give you a minus I omega hx. Okay, and this typically boils down to I mu naught omega hx. So this is our number one relation. And similarly, if you just keep on solving for the other components, so this was for the x component. Now we will do it for the y component of the curl of E, and that if you will land up with something like this. So if it's y, it is z ex x ez, and the right hand side becomes again minus mu naught basically plus I omega h y. And then on the left hand side we keep the z derivative, because that will be dependent on whether it's a positive z or negative z, whether we are in the dielectric or in the conductor. But we can of course solve out the derivative with respect to x is nothing but I kx ez. Okay, so and on the right hand side we again have our standard mu naught omega hy this time. So let's name this as our relation 2, and then we can do the z component, and this will give you the third relation, which actually if you solve it out you will get it as I kx ey is equal to I mu naught omega hz. This will come to be your third component. Please remember that the function is independent of y, so any partial derivative with respect to y goes to 0. So with this we have the first three relations, and the other three relations will come from the curl of h that we have from our Maxwell's equations. So we have curl of h is this, which is nothing but epsilon naught, and then we can actually substitute it right away. So we know that the partial derivative with respect to time will give you an I omega, rather minus I omega e. Let me just write it in a proper fashion, sorry. So this will not be minus I omega epsilon naught e. Okay, and again we will write for all the x, y and z components, and what we will get is for the x component will get hy delta z. It's quite similar to what we had, only the right hand side is slightly different. X. Then so this one will name as equation 4, and then the y component, this equation turns out to be x minus I kx hz is minus I omega epsilon naught ey. Okay, and the third z component will be I kx hy is minus there's always an omega epsilon naught ez. So this will be our fifth, and this will be our sixth relation. Fine. And with this, as you see that we have got 6 equations, and if I actually sort them out, you will find that the equation 2, 4 and 6 are equations which relate hy, ex, ez. Okay, so it has these three components. This is given by these relations, equation 2, 4 and 6, and we have three variables and three equations. Of course, this is enough to solve for the expressions for these components. And this, as you see, has the magnetic field which is in the y direction, and there is no component of magnetic field in the z direction, that is perpendicular to the interface. And so this particular one is called transverse magnetic mode. So this is the TM mode as we know it. Fine. So in the TM mode, what we have is H is nothing but only the y component, and E has x and z. This is how it goes. This is the TM mode. Of course, the other mode that we have will be formed by the other three remaining equations. So I can just rather put another box. So we have equation number 1, 3, and 5. If you look into these equations carefully, you will find that they deal with just the reverse, EY, HX and HZ, which is basically coming from the remaining 1, 3 and 5 equations. Okay, all the odd ones. And this defines the TE mode. What does TE mode mean? It means that the electric fields, transverse electric, right? So it doesn't have a component along the Z. It doesn't have a component perpendicular to the interface. So in this case, your electric field will have only EY, Y cap, while your magnetic field will have the other two components, HZ